All right, so hopefully you got a chance to attempt to try and do this problem. I would go ahead and watch this video and make sure your work kind of matches my work in terms of how to approach this calorimetry kind of problem. So what I've done is I've taken these two problems here that you were attempting, and I've copied and pasted them into these two pages. The reason for that is because I would like to get you into the habit of drawing out some of these pictures to help you to do a better job of understanding like what is in the initial in the cup and what is the values associated with the final at the end of the experiment. So let's go ahead and read through and kind of see what the values are that they give us. It says a 30-gram sample of alloy. So that's got to be, I'm going to just highlight this, a 30-gram sample of the alloy is got to be the metal, right? So that's this thing right here. It is 30.5 grams. This is what we call grams is mass, right? So this is the mass of your metal or your solid. I'm just going to write solid. Okay. Then it says it is at 93 degrees. So this is the temperature of the alloy. Again, this is your temperature, and this has to be the initial because this is at the beginning of the experiment, right? It's at 93 degrees, and it is placed in 50 grams of water. So I've drawn some water in here in blue, okay? And the water is 50 grams. This is clearly the mass of the water. Grams is again mass. And then, of course, you have the water. It is initially at 22 degrees Celsius. So this would be your T initial, but this is for the water, okay? And then it says, the last sentence says, if the final temperature of the system is 31.1 degrees. This is really important to pick up. The final temperature of the system is 31.1 degrees Celsius, meaning that they've measured the water and the water is 31.1 degrees Celsius, but they're assuming that the system, which means the water and the metal or the alloy, are both at the same temperature at the end of the experiment. So the T final is the same. The T final is the same for both the water and the alloy. And this is super important to pick up because your T final at the end of every calorimetry experiment should be the same for both things, the water and the metal. All right, now that we have labeled some of these things, one last thing, it does tell you in parentheses that the specific heat seawater is 4.184 joules per grams degree Celsius. So I've also written that here. This is obviously the specific heat for the water. So the first thing you should do is look at just the water. Step one is always find the heat that is absorbed by the water, Q of the water. So Q of the water has to equal the specific heat, C of the water. So that is going to be 4.184 joules over grams degrees Celsius times M of the water. And if we look above, the mass or M of the water is 50.0 grams times T final minus T initial. So T final, we said, was 31.1 degrees Celsius minus the initial, which is 22.0 degrees Celsius. All right, so all we got to do now is put that all in our calculator. I like to do the thing in parentheses first. So I'm going to do 31. And again, you can see that on the calculator to the right, what I'm doing. I'm going to go 31.1 minus 22.0, and I'm going to get 9.1. So this gets me 9.1 degrees Celsius. Remember that when we're doing sig figs that we would like to keep the one decimal place. So I have that 9.1 there. So then I'm going to go 9.1. So, and we're going to plug that in for our delta T. So we're going to go 4.184 times 50 times 9.1. And I get this number here. I get Q of the water. I want to do that in blue. Give me a second. Q of the water is equal to 1903.72. I am not going to keep all those numbers. I have 2 sig figs for my 9.1, so I'm going to end up with 2 sig figs. So I'm going to go, that's 2 sig figs. I'm going to keep the zeros there as my placeholders so that I get, my 1 is still in the thousands place. And my units, my grams have canceled out. My degrees Celsius has canceled out. I am left with just joules, which makes sense because I'm calculating Q. Q should be in joules. So the heat that is absorbed by the water is 1,900 joules. Again, I need 2 sig figs. Now, it is very important to remember from our previous video that the amount of heat absorbed by the water is going to equal the amount of heat released by the solid, but the sign should be negative because the Q for the solid is released, not absorbed, right? It's exo, not endo. So really, if Q of water is positive 1900, then because of this situation here, we know that Q for the solid is equal to negative 1900 joules. And this is really important in step 2. So this is the number that we're going to carry into step 2. So step 2, now that we have Q for the solid, we would like to solve for the specific heat C for the metal, which is what the question is asking. And I already went ahead and copy and pasted that equation from before. C of the solid is equal to Q of the solid divided by the mass of the solid divided by delta T of the solid. So we're going to go ahead and plug in what we know. And here we'll notice that C of the solid is equal to Q of the solid, which we just solved for, right? We just solved for it. It's negative 1900 joules all over the mass of the solid. Let's look at our picture. The mass of the solid is here, right? They gave it to us as 30.5 grams. And then the delta T is your T final minus T initial. So the final is again 31.1 degrees Celsius because we said the final temperature of the water in the metal is assumed to be the same, minus the initial temperature of the metal, which was 93.0 degrees Celsius. Remember that the initial starting temperature of the metal is not 22, it is 93. All right. So now, again, there's more than one way to solve this kind of question. I like to solve for the bottom first. So I'm going to go 30.5 times, parentheses, 31.1 minus 93.0. And I'm going to get C of the solid is equal to negative 1900 joules all over negative 1887.95. Really, we would like to keep, so if we actually do this in steps, actually it might be better to do that in terms of the sig figs. If we're doing this first, it should be 1 decimal point or 1 number after decimal. So 31.1 subtract 93, and we're going to get 61.9 negative, right? Okay, then multiply that by 30.5. We're keeping 3 sig figs, so we're going to again end up with negative 1890. Remember, so if you look at the calculator, you get 1887.95. We want 3 sig figs, so we're going to round the 7 up, so it becomes negative 1890, 3 sig figs. The 0 is just a placeholder. All right, the units are going to be grams times degrees Celsius. The grams is here, the degrees Celsius is here, right? Okay. Then we're going to divide those two numbers, negative 1900 divided by, negative 1900 divided by negative 1890. And we're going to get this number 1.005291. We're going to only carry 2 sig figs because our 1900 is 2 sig figs. So our C of the solid is a positive value. The negative signs cancel out, so we get 1.0. Our units are joules, grams, degrees Celsius. Okay, and that is the specific heat for our metal in this problem. Okay.